Our final topic in Honors Algebra 2 is topic 12, probability. We will cover the first 4 lessons. Let's first start off by defining probability. Probability is simply the likeliness that an event will occur. We typically focus on what's called theoretical probability, which means all possible events are equally likely. That means your probability answer is always going to be between 0 and 1. The formula to calculate probability is simply a fraction. The number of ways an event, particularly x, can occur, divided by all the ways your events are possible. So here's what I mean by that. We've got a few varieties of common types of probability. You can do things like rolling a die or a number. They call it a number cube, but the same as a die. There are 6 sides of a die, so there are 6 equally likely ways it can land. So we would call that 6 equally likely events. Flipping a coin will either land on heads or tails, so there are 2 equally likely events. If you've ever worked with a spinner, like spinning around and trying to land on a specific location, you can have a variety of equally likely events there as well. It looks like in this case there are 9 equally likely, I'm just going to simplify that, EL events, 9 equally likely events. Now, picking a card from a deck is going to have a lot of options. If your notes didn't print in color, recognize that there are 4 different suits. We have clubs, spades, we also have hearts and diamonds. Now the hearts and diamonds are both red in color. The clubs and spades are both black. If you're not familiar with working with cards, maybe find a template, like maybe do a Google search on a deck of cards and look at images just to see that color coding if you don't see it as well on your note packet. So notice there are 4 different suits, and those would be the suits I described. And each suit has 13 different types of cards. The A is the ace, all the way up to the king at the very end. So there are 4 aces, for example, but there are 13 diamonds. If I held a deck of cards in my hand and I said pick one, each card is equally likely to get. So there are 52 equally likely options. Given a variety of word problems, we'll be able to determine the probability or likeliness of those word problem events happening. Let's first start off with events that are known as mutually exclusive. That means you may have more than one event you want to have happen, and they have nothing in common with each other. You'll know this because there'll be a key word in your word problem. They'll want 2 events to happen, and the word in between them will be and. That means you want one event and another event to both happen. Let's try it out. Sarah rolls a standard number cube and flips a coin. What is the probability that she gets a 3 on the number cube and the coin lands on tails? Let's just work with one at a time. If she rolls a number cube, that means there are 6 equal events possible. She wants to get a 3. There's only one 3 that would make that true. If we think about rolling a coin, or flipping a coin, the coin is only going to have 2 events. And if she wants the coin to land on tails, it's either heads or tails. There's only one way that event can happen. So the probability then of both of these results, the probability of getting a 3 and having the coin land on tails, well, if there's only one event that holds true for a 3 on a number cube out of 6 possible options, we would take 1 out of 6 as that probability. And then and means we multiply. There's only one way the coin can land on tails, but there's 2 possible outcomes. So that would be 1/2, 50-50. If we multiply these together, she has a 1/12 chance or a 1/12 probability that she rolls a standard number cube and it lands on 3, and flips a coin and it lands on tails. Now example 1b just has us comparing individual components to this problem. If Sarah just rolls a number cube, so she's just doing one event, what's the probability her number isn't a 3? So that means we just want probability of not a 3. Thinking about rolling a number cube or a die, they have 6 sides and each side is numbered 1 through 6. If there's a 3 that's on there, how many sides are not 3? That'd be 5. That means she could roll 1, 2, 4, 5, or 6, and those numbers are not 3s. There are 5 ways her event could happen out of 6 possible ways that number cube could land. It's pretty likely she's not actually going to get a 3, isn't it? Then it says, what's the probability that it isn't an odd number? So then that's a little bit different. So we want it to be not an odd number. So that means it could be a 2, 4, or a 6. How many numbers on a number cube are 2, 4, or 6? 3 of them. So 3 out of 6 means she has a 1/2 chance or a 50% chance that she would roll her number cube and have it not land on an odd number. Let's take a look at one more example at the bottom of this page. A bag contains 100 marbles. Or a bag of 100 marbles contains 30 that are purple and 10 that are orange. So that means there must be other colors or something in there that aren't purple or orange to create 100 marbles total. What is the probability that you select a marble that is purple or orange? So or is going to be a unique way to describe this now. So we want just one marble, the probability that it is purple or orange. Or is going to be significant in this process. There are 30 that are purple and there are 10 that are orange. If we want one or the other, we would add those two together out of the total number of marbles possible. That means there are 40 marbles in that bag that are one or the other color. 40 out of 100 would be our probability, which reduces down to 2/5. Or about 40%. Now, you might get that. That might happen. What is the probability then that your marble is neither of those colors? So the probability of not purple or orange. Then we think about all the colors that would be left over, or all the possible marbles that would be left over. If there are 40 marbles that aren't 40 marbles that are purple or orange, 100 minus 40 means there would be 60 marbles that aren't those two colors. It is more likely that you would get a marble that's not purple or orange than you would that is purple or orange. Another option for probability is if you have a non-mutually exclusive situation. What that means is you have dependent events where choices may in fact overlap. Let's take a look at example 2a. It says, let A be the set of numbers 1 through 4, and B be the set of numbers 3 through 7. Now, their union would be all possible choices, almost like the domain, so all choices. And we wouldn't write repetition. So notice in set A, we have 1, 2, 3, and 4. And in set B, 3 and 4 overlap. We won't repeat them, but we can also include 5, 6, and 7. Those are all the choices we have in the union of A and B. Their intersection, though, is what they have in common, or what numbers overlap. There could be an event where nothing overlaps, or if you have overlap, it's likely to be not as big as the number in the union, or as how many are possible. Notice the only numbers that overlap are 3 and 4. Now the number symbol over on the bottom or on the left-hand side doesn't mean we're going to tweet about this like #probability. The number symbol means actually numbers, how many elements there are in a set. So how many elements in a set? We don't actually list them out, we just say how many there are. I know that sounds kind of interesting, we'll see. It says hashtag A, or number symbol A. How many elements are in that set A? There are 4 elements. Notice we don't list out 1 through 4, we just say how many there are. In set B, there are 5 in that set. So 5 elements. Now, in the union, notice we're not going to add 4 and 5 together. The number of elements in the union of A and B is only 7. So that means we have to do something with that overlap. And here's how we'll work with that. If we have elements that are in common in more than one situation, that's called a disjunction. And if we want to determine probability, we have to subtract out those elements that overlap. Here's example 2b. What is the probability that selecting one card from a standard deck is either an ace or a heart? Now remember we said or means we're going to add. And let's take a look at those pictures. If you don't remember what cards look like, you're welcome to refer to the front of our notes. We want the probability that we have an ace or a heart when we pick out of a standard deck of 52. If we look back at that kind of card template, the number of aces is 4. There are 4 different aces in a deck. The number of hearts, there are always 13 in a given suit. So that total would be 17. However, there's one card that's the same in both of them. So there's one card that overlaps. What that means is we have to subtract that one out. So we'll subtract out the ace of hearts for a total of 16. That means there are only 16 cards total in the deck that are either aces or hearts. So therefore the probability would be 16 events we want divided by all the cards you could possibly get, which is 52. And that fraction reduces down to 4/13, or just over 30%. You'd have about a 30% chance of picking a card that's either an ace or a heart randomly from a deck. Independent events are similar to mutually exclusive events. Example 3. A jar contains 12 blue marbles and 8 red marbles. A marble is chosen at random, the color is noted, and then it's put back in the bag. Another marble is then selected. All right, what is the probability that the first marble is blue? Well, there are 12 blue marbles. But now how many are there total? If it says the jar contains 12 blue and 8 red, and we'll assume no other colors are in there, that would be 12 out of 20. And that reduces down to 3/5. What's the probability that the second one is red? Well, there were only 8 red marbles out of the 20 total, and that's only 2/5. Now it asks you, what is the probability that the first one is blue and the second one is red? So and is where our operation comes into play. If we want the blue one to be first, and means we multiply, we want the second one to be red. See what I did there with those colors? Very exciting. We'll take the probability of that first event times the probability of the second event. Now, here's the thing with independent events. The more things that you want to happen, the probability actually becomes smaller. So 6/25 is the probability that both events would happen. And that probability is only about 24%. It's lower than what it would have been individually. All right, part C. What's the probability that both are red? So the probability of getting a red marble, noting the color, putting it back, and getting a red marble again, that would be 2/5 times 2/5, or only 4/25, which is about 16%. So your answers for these, we're just keeping them in fraction form now, but most often you could use fractions or decimals to represent these results. All right, one last example just kind of ties everything together. There is a 30% chance of rain on Saturday and a 40% chance of rain on Sunday. Find each probability. What is the probability that it doesn't rain on Sunday? Well, if there is a 40% chance it will rain, the highest percent total would be 100. So the probability that it doesn't rain on Sunday, we would just subtract 40 from 100, and there's a 60% chance, or 60 out of 100, or 3/5, that it would rain on Sunday. What's the probability that it rains on Saturday and Sunday? So those would be our mutually exclusive or our independent events. We want both events to happen. We want the probability that it rains on Saturday, and so I'm going to multiply the probability that it rains on Sunday. When we multiply percentages together, we actually put them back into decimal form. There's a 30% chance of rain on Saturday, which means that's 0.3 for the probability. There's 40% chance of rain on Sunday, or 0.4. If you multiply those together, there's only a 0.12 or 12% chance that it's going to actually rain both days. All right, let's mix it up. What's the probability that it rains on Saturday and not on Sunday? So the probability that it rains, yes, on Saturday, but not on Sunday, so that includes not on Sunday. So now we just kind of work with these percentages in other ways. It still is a 30% chance of rain on Saturday. But remember, we said Sunday there was a 60% chance that it wouldn't rain, leaving us with 0.18 or an 18% chance of that situation happening. But now look at this. It rains at least one day. Oh, so we've got some choices here. It could rain Saturday and not Sunday, or it could not rain on Saturday and rain on Sunday, or because it says at least one day, it could rain on Saturday and on Sunday. Ooh, there's 3 different scenarios that make that a true statement. How many of you remember what or means we're going to do with each of those options? We're going to add them together. All right, so Saturday and not Sunday. Let's see, do we have that one? We do have that one. That one's 0.18. We found that from over here. That's that option. We know both Saturday and Sunday, that's 0.12. That would be this bottom option. We just need to determine the not Saturday but on Sunday. So if there's a 30% chance of rain on Saturday, that means there's a 70% chance that it won't rain. Yay, that's more fun. But then if it does rain on Sunday, that's our 40% chance. That means there's a 0.28 or 28% chance for that middle scenario happening. Now, if we add all of these together, that's the probability it will rain at least one day. And that would be 0.58, or there's a 58% chance there's going to be rain one of those 2 days. All right, everybody, that's it for lesson 12.1. There will not be a homework assignment with this, so all you have to do is watch this video and submit it for credit.